So I will just briefly remind you that now we will have 2 sessions of working with network data in R. And these 2 sessions will be provided by our colleague, Anna Semenova, who is an analyst and also the very fresh graduate of MASNA program. So Anna, please.
Okay.
The floor is yours, and you should be able to share your screen and so on.
Okay, thank you, Dario. Thank you very much for this kind introduction. Well, hi guys. I'm happy to see you all here. My name is Anna, and you can call me like that. I'm a really resilient MASNA student, and if you have any questions about the program, about my experience, I can surely share some thoughts with you. So I'm really excited to teach you this course, and I'm really glad for my colleagues for this opportunity. So I hope that some of you have this our experience previously, because today we're going to talk a lot about programming, about our basic concepts. So firstly, I want to briefly describe my background. I work in the International Lab for Applied Network Research as an analyst, but also I hold the position of a research assistant in another lab that is focused mostly on public administration issues. So my work for over past 3 years was somehow connected to the social network analysis, and I'm really into this theme, and I think that today we're going to mostly have fun. I hope that we will talk a lot about networks. I'm really interested in your interpretation of my slides. I'm going to show you my favorite networks, and we will try together to understand what's behind these networks, but also the second part of our workshop today will be dedicated to the programming in R. So we will understand some basic concepts. I will give you this gentle introduction to R, and maybe we will install R on your computers, and I will be really glad if you will do all of the procedure and all of the steps with me. So don't be scared. If you do not have prior experience in programming, it will not be so tough for you, because I will start with basic things. I saw yesterday that Marian Kukmas gave you a really hard topic, and I was thinking that maybe some of you will be scared. That's why today's workshop is not going to be really tough. So I hope that most of you come in, and I think that we can start the theoretical part. So again, I will at first give you some theoretical concepts of this topic, and after that we will do some practice. So I will be really glad if you will participate in this class, and I think that it's gonna be really fun. Well, right now I will send you the zip folder for today's 2 sections. So again, section 1 will be more theoretical. We will talk about networks, about concepts, about basic elements of network, and after that we will have fun and see the examples that I have prepared for you. So I will add right now the zip folder of today's sections, okay? It's a little bit big, but I hope that everyone just received this folder. So, okay, I think that I can start my presentation today, and let's start with the theory part. So in your zip folder, you should like open theory PDF file if you would like to go through the slides and maybe see something that you missed. Okay. So great. So let's go ahead and start. I hope that you see my screen right now. And I just want to like tell you something really basic about the networks. So the topic of the class is Introduction to Network Analysis with R. So I think that many people know what networks are. Well, most people know what networks are. For the last 20 years or so, people have like Facebook, Contact, and all the other social media. So I think that people immediately realize what network is because you guys have this experience. So many people know networks in this online context, but networks have always existed actually. Any connection between humans is a network, even if we don't think of it that way. So what people do not realize is that network analysis is a very different type of analysis that doesn't follow the laws or like rules of traditional statistics. Because in the traditional statistics, we have this point, okay? This is a really simple element of an observation. But in the center of the social network analysis, we have a diet. So we have 2 points. And this like simple fact makes this whole approach really different. So this is a separate group of methods that analyzes not only nodes themselves, like I said, but okay, thank you, Daria. We are analyzing connections here. So we are interested in this connection between 2 dots. The important thing that I'd like to highlight here is that the descriptive network analysis can be inferential at the same time. So we can make inferent like conclusions from the picture. And these facts make this analysis and this whole approach really like amazing and interesting. So SNA is first and foremost the knowledge that we live in a really like tightly connected world. So let's start with the outline of this workshop. Today we're going to talk a lot about basic concepts. I will ask you like some questions about maybe something that you know. After that, the second part, the second section, will be dedicated to the R programming language. We will talk a lot about pathways, objects, and like not really interesting things, but I think that they are really, really important. We will use 2 packages in the R Studio. These packages are SNA and iGraph. These packages are, I think, the most common in the social network analysis using R, and these are really important. So in my practice, I used these packages the most. And finally, we will do some practice, and I will show you my favorite examples. And we will have seriously a section that is called having fun. Here we will understand and we will see how Harry Potter characters are connected, and we will see the movie based on the network. So I hope that it will be like more easy and relaxed and fun to make the whole like this educational process really easy and not so scary for you. This is the slide that is dedicated to my favorite textbooks. This is like a really big one, Wasserman and Faust. I think that this is the book of the whole social network analysis approach. So this book like has lots of citations, like thousands of citations. So if you want to have like these really great foundations of this concept, I really like can recommend you this book. This is like the most important thing here. Also, you can find this book in the zip folder. You can like, I really recommend you this book because here you can find all the fundamentals, like a really good practical part of the statistical analysis of network data with R. So I like really recommend you this one. And also I understand that this book is not really popular. That's why I attached this file in your zip folder. So you can do everything by your own. Also, these books are really amazing. This one is more theoretical, I would say. This one is a really practical thing. And the last one is really also great, but this one is based on PAEC program, and Daria Vasilyevna yesterday gave you this introduction to the PAEC program. So I think that she like have told you about it, because it's like really great if you just started to use PAEC. So these are my favorite textbooks, and I recommend you basically the first two of them. Like it's a must. This two is also great, but these two are like you will not find any better. So I think that we should start with really basic things. I understand that not all of you have this prior experience with network analysis. That's why I decided to start with the very foundations of this concept. So here you can find and see the network. To construct the network, we should have actually two things. We should have a list of nodes. These black dots are called nodes, and we can use other words like vertices or actors in social network analysis field. Researchers and practitioners or more often use like this actors notation. But also you can just use these words interchangeably. So you can say that like in this network there are 14 vertices or 14 actors or 14 nodes. So please like remember this, because I will ask you some questions about my favorite networks further in this first section. So I would like you to forget about these gray circles here and like concentrate on the network patterns here. So the whole thing here is called network, and also we can call this network a graph. And there are some differences, yeah, between these terms. But in our workshop, you can use these two words interchangeably. So you can say that we have here a network, or we have here a graph, and it will be like, okay. So after that, you should remember that we have, again, nodes, vertices, or actors. These are these like black dots. The second thing that you should have to construct your network is like this thing, is links. So you can call these lines here links, and this is the safe words. So if your link is not directed, this link will be called an edge. So this link here are edges because they do not have this direction. But if your network is directed, you will call these links like arcs. Okay, so if you do not want to bother with this direction thing, you should use links or ties or maybe relations. This word is also really common in the social network analysis thing. But if you would like to concentrate on the fact that your links do not have any directions, you should call them edges. Like here we have edges, but if you will have this direction right here or right here, or like in any place here, you will call this relation an arc, and your network will be directed. Also, let us see on these gray circles. Here we have 3 communities, and there are lots of algorithms that you will use later, in this workshop to find these communities. But mostly we have the algorithm that calculates the highest modularity that captures the optimal number of communities. So we will talk about it later. And finally, the final really important word here is adjacency matrix. This is a really common form to represent the network data. And we will use this form of representation later. But the synonym for the adjacency matrix is socio-matrix. Okay, so you should remember this words, and I will ask you some questions later. So the question that I often ask is, why did Moscow become the capital of Russia? And I totally understand that there are lots of historical theories, it's a really interesting and intriguing question. But in social network analysis, we have our own theory. Why did Moscow become the capital of Russia? So if we imagine that our cities are nodes and our rivers are lanes, we will have this picture. And you see that here we have a network, right? And this network represents straight roads in the 12th and 13th centuries. And according to this theory, Moscow has become the capital of Russia because this city holds the central position. So if you would like, for example, to go from city number 2 to city number 25, your path will be, Moscow will be included in this path. And if we calculate this shortest paths, for example, if we calculate the shortest path between city number 1 and city number 24, and if we do this procedure many times, and again, we're interested only in the shortest path, which is also can be called geodesic. It turns out that Moscow lies larger number of times than other cities, and that's why this city, according to this theory, again, it's not really historical, and it's doesn't use these traditional methods of history, but according to this theory, Moscow has become the capital of Russia because it possesses this central position that is really, really important. And you see that you can represent the map of our country using network. And during this workshop, I would like you to know that you can imagine like simply everything using network, like your classmates, for example. If you like have this connection, like if you're friends, you create a connection and you can understand like literally everything using networks. So I think that this theory is kind of cool, and it gives us really an alternative perspective on the whole history paradigm here. Also, one of my favorite example of social network analysis is this research made by Moody. And here you see that here we can see the social structure of countryside school districts. And we see that according to the connections, I think that students created previously, we can say that some groups and some grades are more connected than others, but in general we can see that they are somehow mixed. But according to the race they have, we can say that there is like some sort of segregation here. We can see that white people make ties with white people, and Black people make ties with Black people. And in social network analysis, this can be called homophily. So we can see that those who like has this attribute called white, they form ties more often, and this is a really like crucial concept in the whole social network analysis. But you see that this mixed race is represented like everywhere in the network. But you see that grade is not so important. So people make ties based mostly on race. And also we can model this network and prove it statistically. But even from the picture that we have, we can make like some inferences, and that's the beauty of social network analysis. You can make inferences based only on the visualization that we have. And I really like this picture, and I think that it like gave us, it's like creates the whole understanding of the social network analysis, the possible ways we can use this analysis. Okay, I want you to here see on another example. Here we can see, this is the source of this example. Here we can see the agar network. This is a really like specific type of networks, and you see that here we have this central node, and we have like all of the connections here based on the central node. So to like easily understand what the agar network is, I can ask, for example, you, what friends do you have, for example? What ties do you have in general? So maybe you have like this husband's family cluster, and you see that this is the this purple color of this cluster. Here we can see that this person has electronic literature cluster, family and friends and all the other things. And you can easily imagine this picture based on your conductive friends, for example. And you can do it actually, and it's not like really difficult. And based on my experience, it turns out that this community detection algorithm works quite nice. So this community detection algorithm found that actually I have two distinct communities based on my connections. So I have a really like tightly connected part based on my school friends, and also I have like really simply the other parts based on my university and connections that I've made here. So I think that this picture is quite nice because the visualization that we have here is really like great. I like the colors, I like the layout and all the other things. So next, here we also have Ego network. And here we can see that this person, David Gilbert, this person has like different communities, and we can see that this community, like blue one, is tightly connected. The pink community is not so tightly connected, but it's interesting also here that these two communities are linked between each other. And also interesting that this community, like orange one or yellow, whatever, is like really like separate from all the other communities. So I have a theory here. So let's think together about it. So I think that this person maybe came from a really distinct part of like the world, and these people that he like had previously, they cannot be like connected to all the other guys here. Maybe these like notes or actors are friends, and these like notes or actors here maybe colleagues. So we should like think about it. But if you want to like have the true understanding of this picture, you can just go to the source. So, well, can I ask you please to help me with the interpretation here? Here, I used this picture from the source that was written in 2004, that is called Chains of Affection, the structure of adolescent romantic and sexual network. So please, someone be so brave and kind to interpret something that I have here. So, okay, I can
love triangle.
Sorry?
Maybe it's a variation of love triangle, but with another figure, like not triangle, but some love line or something like that, if it's the relation.
Well, it's interesting. I think that you are right. But you see that here we have this big parts of our network, right? So if you will go into the network analysis further, you will call this network the largest component, yeah, the largest component of our network. And you see that we have this part of our students that are somehow connected. So here we have like a mutual dyad here that is really far from the other nodes. So these two people here, they do not form any other connection except each other. Okay, so maybe this is like, yeah, they can be married. So maybe maybe even you like have this couple who like dating for 100 years, and this is literally this couple, and this is quite interesting. But I was like, this is like a really great love story here. 63, great. But what is the most surprising for me here is that we have this circle. Okay, so we have like some people here that forms this really interesting circle, and we have like some people that are included in this circle, and this is like quite interesting also. So I think that here the most interesting and like really lovely part is this dyad, and also this big one. This guy is a legend. Yeah. Seriously, yeah. So you see that this guy is like really popular. So this guy was dating like with many girls. Yeah, it's not like really great love story, but we can say that this is this really popular guy. Why do we have edges, not arcs here? We can't really understand who likes who. I think that here, if there is a connection, so if a link is present, these guys were dating. It's like marriage ties. We do not have these marriage ties do not have this direction by nature. So if one person is married to the other person, who is married to whom? So we cannot have this direction here by nature. And for example, well, what do you think? Can friends have this direction? Can friendship ties be directed? What do you think?
Probably yes, it can, because one person can say that this person is his friend, but another person might not say so, because people are like relate to each other differently.
Yeah, you're right. But at the same time, if we consider like Vkontakte friendship network, if I actually do not remember, it's quite.
In case of social networks like Vkontakte, it cannot be so, yeah, but you can only be directionally subscribed to somebody. But if you're friends, it is like undirected network.
Okay. So it depends on like the method that you will choose. But like originally, we have this really popular data set, Medici data set, Florence business marriage ties. And according to this very popular data sets, we can say that these marriage ties are not like directed by nature. I can understand something with friendship, because if one person like really would like to have a tie, this friendship tie with the other person, well, I can understand that. But if you're married, it's like a ritual, and you just have like the something in your passport. Like I do not imagine the situation if like one person doesn't know that he or she is married. So I think that it's something like that. So maybe if one person nominated the other, we have this link here. Okay, so let's go further. Thank you guys for your help and for interpretation. It was really like funny. Okay, So this is another great example of social network analysis. I really liked it because not because this research was made by my colleagues Daria Vasilina-Maltseva and Vladimir Batagir, but I think that it's really great. So this research, this study was based on social network analysis of the whole fields. So maybe you previously heard about bibliographic approach, bibliometrics. This is literally the citation analysis. Okay, so if one, for example, paper is cited by the other, we will have this connection. And if one like paper or research or whatever is citing the other, we will also have this connection. And you see that we can understand the whole process, how the whole sphere is developing through time. And I think that it's quite interesting. And this is something that you can do based on like not really advanced procedure. And this visualization and whole analysis approach was made using Pike. So, okay, we have here another picture. This picture represents drug consumption, drug consumption in high-risk cities. Well, what do you think, guys? What do we have here? So let me help you. Here, let us understand what do we have here. So we have here drug users, So if one person, Maxim, wait a minute.
So I wanted to interpret that network. So I believe that we see here very small white cluster, and predominantly there are two clusters that use that make up most of the drug users are Puerto Rican cluster and African American, but there are sparse connections between Puerto Rican and the African American cluster. So we have only, I believe, two links. No, not links. Two arcs. One from Puerto Rican and one from African American to Puerto Rican.
Well, you're good. You're really good. And this is like brilliant interpretation. And I also liked the Sarah one. Sorry. Yeah, actually, Maxim and Sarah were right. And I just want you to understand and pay attention to the fact that we have like really important guys for us. Here we have like this drug user and this drug user, maybe this one. If we imagine that they like do not have this connection, this part will be disconnected, okay? And we can consider these guys as important ones. And if we dig into the details later, right, during our practical part, we will say that based on betweenness centrality measure, these two guys are really important because the shortest paths between all the nodes that we have here, they lie higher times, larger number of ties within these two or like three guys. But basically, you're right. And according to this attribute, so again, guys, here we have a network, right, or graph. You remember that we can use these words interchangeably. And also Maxim was right that we have here arcs because our network is directed. And here we have, for example, mutual ties right here and right here. But here you see that these ties are not mutual, they are asymmetric. We will call them asymmetric. And according to this network, we have attributes. So we have actually one attribute here. So we have this basic network structure. And additionally, we have like some property. And this property is race. So here we have three big like parts. Here we have our nodes. Here we have our links or arcs, as Maxim said us. And also we have here attributes, this race one. So according to this simple visualization, we can make again some inferences based on the network consumption. And I think that if this network is quite good, and if you would like to read about this network consumption in details, I gave you this source. Okay, so do you have like any comments here? Maybe someone would like to tell us something. Okay, let's go further. Well, this is actually really great also example that I really like. This is the political blogosphere in the 2004 US election. So basically, this network is based on Twitter replies, if I do not mistaken. Okay, so according to this Twitter network thing, we have this segregation. So we actually have here two separate clusters. And we can say that those who are from like a Republican right party, they tend to communicate with each other, whereas those who are not from this party, they tend to communicate within each other. So there are not quite dense connections between two separate clusters. And also I recommend you to like read this paper. It's not really difficult and it's not so advanced. So you will totally understand it if you do not have this prior experience in R. Well, this is the last example that I really like. This example is based on types of wines. And I think that it's really great because here we have two types of connections. Here we have this parent-offspring connection and sibling or equivalent. And maybe you know something here. Well, I think this Pinot Noir is quite popular, and maybe someone knows this type of wine. And you see that actually the majority, if not all, wines are like originally created from one type of wine. So this type of wine that actually I do not know is like a really important based on this network structure. And you see that here we have Riesling and all the family like that is connected to Riesling. Also we have here, I don't know, maybe you see something familiar. Well, I know actually Chardonnay, maybe, yeah. It's really, it's also really common. Yeah. And you see that all of these types of wines are originally, yeah, Riesling right here from one sort Yeah, and I think that's also really great. And also I give you the source of this research. Okay, this part was like really fun, but network analysis, it's not about, it is about funny networks, but to understand all the network things, you should understand some basic concepts, and I can assure you that they are not really tough. Terminer means an important member of the family in German. Well, this is interesting. I actually don't know the translation of this word. Great. Okay, so let's talk about some basic concepts that we have in social network analysis. So here we have like some basic and really common notation that most of the scientists, I would say, use. So we have a network, and this network is this network consists of some properties. A network consists of a graph that represents the vertices and links here. V is the set of nodes, A is the set of arcs, E is the set of links, and you see that here we have basically links, okay? So to make a graph, you should have these two properties, because if you have like only lines, you cannot build the network. You should have both. You should have vertices and you should have these links. Also, we have here like link value functions and nodes value functions, and these are not really like important as graph. So to build a network, you should have a graph, but these two things may be absent. So if two vertices in a graph are connected by an edge, we can say that these vertices are adjacent. A really important thing here. If a vertex V's endpoints of edge E, we can say that they're incident. So these adjacent and incidents are really like basic and really important concepts in the whole network analysis. So I gave here a hint. Two vertices are adjacent if they share a common edge. Two edges are incident if they share a common vertex. Well, is it clear for you, or we can like discuss it in details?
Yes, can you please explain like the edge and common vertex maybe on like a visual example?
Yeah, sure.
Would be called adjacent and which incident?
Okay, can you see? Well, I should stop sharing my screen and start new demonstration. Okay, so can you see my screen now?
Yes.
Okay, so I think that we can construct here like a network, and I think that it's really like easier for you to like see this picture, and you will understand everything. So okay, we have like, let's create 3 nodes. Here we have like nodes, okay, and also we have connections. So we can create this connection from one vertex, from one vertex to the other. And let us carefully, okay, so carefully understand, let us name this vertex like 1, 2, 3. Okay, let us carefully again read this interpretation. So two vertices are adjacent if they share a common edge. So what do you think? Which vertices are adjacent right here? some
1 and 2 and 2 and 3.
Yeah, you're good. So these vertices, right? So nodes, vertices, these words are basically the same. So vertex number 1 and vertex number 2 are adjacent. Okay, so we can call it about adjacency only like about vertices. These two vertices are adjacent, as well as these two vertices. So vertex number 1 and vertex number 3 are adjacent because they're connected, or they share a common edge. So we can say that these two vertices are adjacent, but we cannot say that vertex number 1 and vertex number 3 are adjacent, okay, because they do not basically share this edge. And in the same manner, we can talk about edges. So two edges are incident if they share a common vertex, okay? So what can you say about incidency here? Which
Node 2.
So two edges are incident if they share a common vertex. So these two edges are incident, right? Because they share this common vertex number 2, right? Okay, I think that it's quite clear. It should be clear, at least for you now. So this thing here, we can call this like graph on that. We can call this thing a network or a graph, right? So if we do not have like additional properties, this thing will be called a graph. But if, for example, we will have like attributes, like this is a male, this is a female, let us paint it in like this pink color. So if we have this picture, this will be a network, okay? But if we have like a really basic structure where we have only nodes and only links, that's it. This will be a graph. So graph is a basic structure and network is something with additional things, but we can call graph a network. Okay, I think that it also should be quite clear. So again, two vertices are adjacent if they share a common edge. Okay, and we can say here that vertex number 1 and vertex number 2 are adjacent because they have this edge. And also we can say that two edges are incident, yeah, right here, if they share a common vertex. So these two edges are incident because you see that here we have this common vertex number 2. Okay.
Thank you.
Can a single network have nodes of different labels? Yeah, actually, it is possible. The most like common example of your thought is two-mode network. For example, the really common example of this network structure is, let us paint it. For example, let it be blue, and if, for example, okay, let's consider the example. Please carefully read the question from the chat, and I think it's a really important one. So let's imagine that we have like students, for example, let me choose someone from the chat. For example, we have here Yaroslava, we have here Maxim, and we have here Sarah. Let's imagine that you guys went to some conferences during the summer. For example, our summer school or like other conferences. And let us build this conferences thing. So you see that conference 1, conference 2, and conference 3. And you see that this, here we have 2 groups, of vertices. Let's be like red, not pink, not to mislead you. You see that here we have students, like here we have Yaroslava, here we have Maxim, and here we have Sarah. And let's imagine that, for example, Yaroslava went to conference 1, but also Yaroslava is quite a really good student, and also she went to the second conference. And you see that here we have 2-mode network, and actually my master thesis was dedicated to the analysis of this type of network structure, and it's quite interesting. And the matrix, this network structure can be described by incidence matrix. That is also quite popular in social network analysis. We can say that, for example, if Yaroslava is really great student and she would like to go for PhD, for example, she maybe went to all of the conferences that maybe took place in your city. So I think that you got the idea. The very important thing here is that we cannot have connections between the guys and between the conferences, because guys go to the conferences. We cannot have this connection here, but we have these connections here. It means that number of possible ties is lower than in 1-mode network. So if we consider only one group of people, this network will be called 1-mode network. Okay, it's the most common, and all of the methods, the majority of methods are developed to this type of networks. But also you see that we have here 2 groups of nodes, and also we can have 3-mode network, 4-mode network, but they are not really popular actually, because we have specific types of approaches that we can use here. Sorry, wait a second, please. Okay, I closed the window. It's really loud. So did I answer to a question?
Yes, thank you.
So yeah, let's continue our talk about networks. So if you guys will have any questions, please don't be so shy, and I will try my best to give you an explanation. So you see that here we have different types of networks. We just consider 2-mode networks right here. Students go to conferences, easy to imagine, okay? Also, we have multi-relational networks where we have different types of relations here. Also, we have temporal networks, the dynamic graphs, the networks that are changing over time. Also, we have eganets, and we also considered this type previously, okay, where we talking about examples. Okay, so, but you see that the majority of the networks that you will work with will be 1-mode networks, okay, where we have one group of nodes, like students separately, conferences separately, and the main procedure that lies behind these 2-mode networks is to create at the end of the day, yeah, one mode network and work and apply classical methods to analyze this network. Okay, so here we have like two really important concepts. The first one is a dyad. The dyad is basically two vertices. Okay, so they can be connected, they can be disconnected, but the dyad represents a pair of actors, like a pair. It should not be always connected. We should consider a pair. So A and B separately, it's a pair. A and C, it's a pair. Okay, so it's a pair of actors and the possible relational ties between them. So this tie can be like connected from A to B. This tie can be mutual from A to B, from B to A. It can be like absent, so we cannot have like here the connection. And yeah, there are all possible ways to represent the connections, yeah, between A and B. Also we have these triads. So triads, it's the smallest social structure. We can call something a network where we have like three vertices. So starting from 3, we can call it a network. But if we have like only 2 vertices, this dyad cannot be called a network. So if we separate here A and B, we cannot say that this is a network. It's just a dyad, it's A and B. But if we consider A, B, and C, we can say that this is a network. And we can apply some methods and like all the tools to analyze the network structure. Spoiler, it will not be so interesting, but we can do that. Okay, so 2, not a network, 3 is network. Okay, so there are lots of really possible triads here. If your network is directed, there are 16 possible triads. Here we can see all the combinations we can have between these 3 nodes, yeah, 3 vertices. I will use all of the words interchangeably for you to understand that we can name it vertex, we can name it like node, and it's all okay. Actors, maybe, if we consider like social relations. So if your network is directed, you have like full list of all possible triads. But if your network is not directed, we will have only 4 possible types. So we can have this null triad, or we can have like this full triad. We can have like the mutual ties where we can have this type and this type. These are the 4 that we can consider. So we can sometimes we use these triads, dyads to calculate some general statistics that our network has. For example, we always use dyads to calculate density of the network. So you see that here we have this density thing. It's a really important one. So graph density, this parameter represents the ratio between the edges present in a graph and the maximum possible number of edges that graph can contain. You see that not all the connections are present. We do not see the connection between A and C, as well as we do not see the connection between C and B. But if we consider all the possible connections, like if we create a full graph where all the connections are present, we can count the number of dyads, and we can say that, okay, in our network, there are like, for example, 60 dyads, full dyads that can be constructed, but our network has only 2, for example, yeah, not 2, but 1, 2, 3, 4, 5, 6. Here we have only 6 connections, but possibly the full graph will have, for example, not 60, but okay, 20. But if we have only 6 out of 20, we can say that, okay, only a small like percent of all possible edges is present, and it gives us something, it gives us understanding about our network. And this information is really like important, and we always use this density parameter if we would like to describe our network, because we can have like different types of networks. These networks are really like unique, and the density of this network will be like really different. But we cannot compare this density, because you see that if our network has lots of vertices, like thousands, number of possible dyads will be also really big. But if our network, for example, consists of 5 vertices, if we have only 1 out of 5, it will be a lot. It will be like 1.2. It's like 20% of all possible dyes are present. But you see that in this type, in this situation where we have lots of connections and lots of vertices, the density will be low. And with the increase of this number of vertices all over, and this is quite obvious, I think. So you cannot compare density of this network, for example, with this one, okay? Because here we have like a lot of like a really big percentage of ties that are present. So this is really important thing that I always tell my students to do. And also we have transitivity. This transitivity parameter is also can be called a clustering coefficient, and it's also quite popular. And we use like these 2 parameters to understand, do we have this clustering tendency? So do our network has this tendency to create these triangles or not? Okay, so let's go further. These are really basic things, and I hope that you understand them. And I think that this is like the one of the last slides that we will consider today. I hope that you are not bored, because these things are really basic and you should understand them. Well, let's consider another like very important things that we use in the social and network analysis in general. Here we have this geodesic thing. Well, geodesic is the distance between 2 nodes, not like the simple distance, but the shortest distance. Well, can you tell me the shortest distance between nodes A and node D? Please consider the direction here. What's the
4.
Yeah,
It is 4.
it is 4. So 1, 2, 3, 4. Okay. But if, for example, well, it's like the only possible thing, and the only possible way to go from A to D. But if, for example, we consider this network about our Moscow thing, you see that we can go from node number 4 to node number 25 by many directions. For example, we can use this shortest path, for example, from 4 to 3, from 3 to 11, and like in this manner, we will go from node 4 to node 25. But if we do not in rush, we can go from nodes number 4 to node number 3, next to 2 to 1, and yeah. And sometimes, yeah, we are interested in the shortest paths, and this idea lies behind the centrality, for example, between the centrality. And sometimes we're interested in this shortest path, and this shortest paths are also called geodesics. Okay, in Russian, it's also called geodesiki, as far as I remember. And this is like really important concept in the whole social network analysis. And you should like remember simple fact that geodesic is the shortest path between two nodes. Okay. Also, we have like the length of the walk. I actually do not remember who told us that we have here 4, but this really brilliant mind already understand the idea that if we have like the number of ties that we went through, so to go from node number A to node number D, we have to like go through 4 links. That's why the length will be 4. So from A to B, 1, 2, 3, and 4, and the length between these 2 nodes will be equal to 4. Okay. Also, we have the diameter of a connected, it's important, graph is the largest geodesic. So it's the largest shortest distance. Okay, the largest shortest distance. For example, if we consider this Moscow again case, we can say, for example, that to go from this node to this node is only 2, and this is the shortest path. But if we calculate all the shortest paths between every pair here, between our nodes, we will we can actually find the largest one, the largest shortest path, and I guess that it will be like this one. Okay, from 4 to 25. Yeah, you got it. So, well, first, it can be misleading, but if you understand this longest, shortest path, you will be okay. So, the final words for you today. Sorry, guys, for this long and not really maybe fun, as I told you in introduction, but the final word for today will be a component. Okay, the connected subgraph in a graph are called components. For example, let us calculate the number of components right here, because we have like separate parts that are disconnected totally. Here we can say that this part is a component. This part is also a component. This part is also a component. And if we imagine that we have a separate isolated node, it will also be called a component. So you see that, well, mostly when we are doing social network analysis, we are interested in this giant component. Okay, and here this component is quite interesting for us. Okay, but sometimes we are also interested in the isolated one. So here we have, let us calculate the number of components. Okay, so this one here. So basically we are counting these isolated subgraphs here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. The largest shortest path reveals the most distant items that are still connected in this very network. Did I get it right? Well, yes, I think that your explanation is also great. So the most distant items, yes, sorry, you're right. And I think that is great remark here. So we are basically interested in the most like really far nodes from each other. So, but it's important that where we can consider this node only in a connected network. For example, if we have here disconnected parts, we cannot calculate the geodesic distance. So here we can say that this, for example, two cities are really far from each other, because it takes like 1, 2, 3, 4, 5, 6, 7, 8 rivers here, right? To go through. Maybe it's a one river, but you should go through like 1, 2, 3, 4, 5, 6, 7 cities to go from this city to this city, and I think it takes like several days. Okay, so let's continue. And finally, I have this slide for you, and after that we will continue with the practice. Okay, so just please pay attention to this slide, as it is also really important. So as I said, we have this network, like basic network structure, where we have only nodes and only links. But sometimes we have, for example, some attributes. If we create a network of your friends, for example, my friends. Okay, so let's create and imagine that we have a network of my friends, but we can also collect some data about attributes. Maybe if this friend is a female or male. And if we have like a really small number of categories, we should understand how we should represent this attribute. So if we have a small number of like categories within our attributes, it is like better for you to use color. For example, let's consider this example. Here we have only 2 categories. We have male and female, and we can change the color of our nodes to represent such a structure. But sometimes we have, for example, continuous attributes like age. If like one person is a really old one, how can we color this network based on age? Well, we should either like make these categories like less than some thresholds, or like more than some thresholds, and we can use this information to use color. But sometimes if you would like to like add continuous attributes to your picture, to your analysis, you can change the shape of your nodes. So if, for example, we would like to add age as an attribute, okay, in our network, we will say that the bigger the nodes, the older a person is, okay? And also, if we consider like this continuous data and continuous attributes, we can also think about, for example, salary, for example, of a person. So is a person like has a really big salary? Yeah, we can also put that information in our network. But again, if you have continuous data, it's important. It's better and safer to use like the size of the node. But if you have like a small number of categories, like here and here and here, you see that the best way to work with these categories is color. You see that here we have 1, 2, 3, 4, 5, 6. We have 6 categories, and the color is like great, and it's the best way to understand the structure. Also, you can change the shape of this node. Here we have circles, but if, for example, you would like to add race and, for example, sex, you can use color and shape. So you can add several attributes again for our network. Okay, this is pretty much it. And I hope that everything that I have told you is not like really difficult for you. I have like tried my best to give you this gentle and really fun introduction to this network analysis course. And again, if you have any questions, please do not be shy and please interrupt me and ask me something. But if you do not have any questions, let's have a break now. And after the break, we will continue with practical parts. So we will construct some networks. We will talk a little bit about programming using R. I hope that most of you have R on your computers. And also we will have this really funny part when we like play and construct these dynamic networks, and we will even construct a movie based on networks. So I think that it will be fun, and yeah, let's meet in 15 minutes.
Anna, Anna, thank you so much.
Mhm.
Yeah, the only thing is that we have a schedule, and our next session will start at 6:30.
6:30. Okay.
Yeah, because some people can come exactly to the next session, so it would not be honest to start before.
Sorry.
Probably now there are some questions of our installation or something like this.
Okay.
Probably we can use this time like 7 more minutes to briefly discuss it.
Okay.
And then we will go to 15 minutes break, and then at 6:30 we will start the second session.
Okay, great. So I think that as we have like some spare time, we can talk about R. So I have created some like really helpful materials for you. I have created this handout. So I try to like create the whole procedure, the workflow for today's section, and you will find all the explanations like from very beginning how to use R, and after that we will play with the networks. You can also understand something about the sources, the data, and I will tell you about it further, like in our practical section. But I think that we can actually use this time to install R for those who like don't have this program on their computers. So you see that to install R, you should firstly install R, and after that you should install RStudio. So you should basically Google something like R install. It's like really easy. And you should go to this website called runrproject.org, and you should like install R for Windows, or like if you have Mac, you should use like another link for the installation. And you see that here we have like a really helpful website that is called our project. And you see that here we have like lots of countries, and you should use your own country. But as for me, I used UK, okay, for this installation. I will send you the link, but it's not like a really, there are not a lot of differences between all these countries, especially for now. And after that, after you install R, you should install RStudio. And I will send you also a link for this program. You see that here we'll have a really simple guide. Firstly, we should install R. After that, we should install RStudio. It's like not really difficult. And here we have like download R for Mac OS or Windows. Well, probably I should add this link for you guys. Can I delete this? Okay. Can it be? Still see message. Okay. So you can use like the link that you prefer here, but for the RStudio, I recommend you to use this link. Okay. Oh. Okay, so this link, the final link is for RStudio. So actually, I have a guide somewhere on my computer. Let me find it, please, where I have all like the special information for those who like do it for the first time. Now is this? Guides to install. Yeah, I got it. So my dear colleague, Stanislav Pashkov and Valentina Viktorovna Kuskova, they have created this installation guide. So I will add this guide also in the chat, okay? And I hope that it will be really handy and useful for you. Okay. So I recommend you to use this guide, okay? Because here you will find also all the links, but I hope that most of you like have R on your computer, but if you do not have R on your computer, it like will take you 15 minutes to set the workflow for the further analysis. Let me demonstrate you this guide. Here you see that firstly you should download R, and after that you should download RStudio, not vice versa. And after that you will have the opportunity to like work within R, and you see that this is how R is like R looks like, and we will work in this using this programming language today, this software RStudio. Okay, so after that, after the successful installation of these two things like R and RStudio, and you see that R is a really old program, and let me show you how the original R looks like. And basically this is R, and you can like make some comments here, for example, 1 + 1, 1 + 2, 3, but this RStudio is like a good looking version of the same thing actually. And we can create some like objects. For example, we can create a vector And if we create a vector in the RStudio, we can see this object right here in the environment. But if we use this old version, not old, but old looking one, you will not have this opportunity. But if we press A here, we can see that this is actually a vector that consists of three numbers here. So we will use RStudio because we can like create scripts here. We can write some comments and we can see the environment, but it is also possible to use R. Don't save. Okay. So after that, we will like work further, and we will install like packages. And here you can see that we have like special steps for Windows users, special steps for Mac users. And I again would like to thank Stanislav Parkov for this really great installation guide. Okay, so after that, so it's like not really a tough one. So after that, you should like put here all the free versions, because we like it's like a really free and easygoing one. But you should stop here. You do not like you do not need LaTeX right now. But if you want to create this nice looking handouts like mine right here, let me show you again. Summer school. So I have prepared this really nice looking handouts using R, and I used LaTeX in my computer, and you see that you can do just simply the same thing to create this output, really nice looking one. And we will discuss all of the steps like in a few minutes. Okay. And I think that it will be really like interesting for you. And you see that we have here lots of pictures, and we will discuss all of them for sure. Maybe you guys have some questions about our installation. Maybe we can consider some questions from you. Maybe you have some problems, and we can also discuss all of them today. So please, again, don't be shy to ask them. Okay. Are you guys here with me?
Yes, everything is just clear.
Okay, great.
I think we should make a break because Anna, you also need some time to have some rest, at least like 10 minutes.